So on the topic, slightly changed a little. At first, I thought I would be doing this for a general population of for incoming students, and I wanted to make it kind of fun with more pictures and not require much math. But then, since it's at the math T, you know, that's much more fun. So I went into the math and didn't have time to do a lot of the other stuff. So I think this, what I'm hoping this is that there's at least one person here, maybe a data science undergraduate or somebody that's going to learn something from this today. That's really the goal. Maybe, I think maybe everybody could learn a little something, but it's more aimed to that than just sheer entertainment.
That Priyanka tested most of them.
You have a question? You had a question? Okay, yeah, if you have a question, just ask. Hi, Sojun.
So I think there's just the one. Yeah.
All right.
Hello, it's really nice to see you again.
Okay, so what does a Monte-Carlo simulation tell us? So a little bit about the origins of this math and everything is that so hold on, I'm just having trouble. I'll be fine in a minute. I'm just having a little, okay, there we go. I need to get the bar out of the way of the screen. I guess I have to move it when I want to see the bottom. Okay, so in the 17th century, in the second part of the 17th century, Bernoulli, who was Swiss, actually stated and proved the first form of the law of large numbers, really the weak law of large numbers, which is the version we're going to talk about for our simulation today. He also made contributions to calculus, and his brother Johann actually is the guy that proved L'Hopital's rule. That was not L'Hopital, who was merely his patron. So this was a big, prodigious mathematical family in the late 1600s, middle to late 1600s. This guy did a new mathematical proof of this when people weren't even thinking about it. So he discussed simulations performed by filling a sack with different colored pebbles, two different colors, or maybe one color and other, something like that. And then trying to get the, okay, there we go. Okay, right, there we go. Okay, and then drawing from the sack with replacement, which is just flipping a coin, really. Only you can now control the exact probability. It doesn't have to be a half. So if you put 300 black pebbles and 200 white ones in, and you select and you count white versus black, you should get a rate, or black versus white, you should get a ratio that's 3:2, or something that looks like 3:2. This is what he said. Let me go to the next slide. Yeah, so the first paragraph here is, he said that even without any education at all, and he actually said something more cruel than that, anyone would feel this ratio would approach 3:2. He found this very interesting, the fact that anybody would feel that way, very interesting. And he felt that this was not an educated, not something that's learned, but something that's felt. This is one of my theories too, is that probability is a subject, has three components to it. It has theory, application, and intuition, and that you need all three really to, you need to develop all three to appreciate the subject. I saw that written later by William Feller, and I thought that sounds right. So he wondered if there was any, so he thought everybody would know this, that if you kept pulling the pebbles out and putting them back, taking them out, putting them back, you would get a ratio that's 3:2. But he wondered if anyone other than himself supposed that there would be a limit here, that if you did it indefinitely, you could get arbitrarily close to 1.5 or to 3/5 if you're taking the fraction of the whole. Okay, so although the concept of the law of large numbers was written on in the 1500s by the physicists Cardano and Kepler, and maybe non-Western mathematicians, Bernoulli did more than anyone knows. He really formulated it mathematically, and he did a proof of it. His proof's very long. It involves some things from number theory back then and several different lemmas that he combines to do the proof. The modern proof, the one I know, takes 3 lines, I think. So I've never made any progress reading his proof. It's interesting, but it's just not something particularly top priority. Any questions? Are you there?
You know, I have to say, I had no idea that L'Hopital's rule is actually Bernoulli's rule. That's pretty cool.
Oh, his older brother, Johann.
Oh,
Yeah,
Johann,
I think
yeah.
so.
Yeah.
Yeah. Yeah, L'Hopital was his student. You know, he was a rich French marquis.
Mm-hmm.
Yeah. Okay, so that's my understanding. Yeah, a little more. So his work, Bernoulli's work didn't show up until after he died in 1705 in his treatise called Art of the Guess. He was reputedly lazy and by his own description, and he thought about this for a long time before he showed it to anybody, and he didn't even really show anybody. His nephew, he showed it to his nephew, but he didn't publish it during his lifetime. I find this stuff interesting.
Mm-hmm.
So after this, though, the ball kind of dropped on this. And I think because he kind of took it all the way in one sense. We really needed a lot more before we could get to the stronger law of large numbers, which came much later, like around 1900. So what happened is the central limit theorem, which says that all distributions, all means approach a distribution that is normal under certain conditions, that took over, and that a basic proof got done for that around 1715, and then a strong proof got done for that, pretty strong, by Simon Laplace around 1795. So that became the central idea in the 1700s and even the first part of the 1800s. But then the LLN took over. It has a very important place, a very, very strong place in mathematics and in statistics and probability, as the central limit theorem still does too, of course. They're the 2 big ones. All right, so what is the Monte-Carlo simulation? Trials are performed in which the conditions are held fixed from trial to trial, picking pebbles out of the bag. We assume that no new pebbles are added, that nothing's changing, people aren't looking at the pebbles. Pebbles taken, put back, shuffled, no one's looking, take it, but those seem fairly independent. I write that trials are independent. The outcome of one trial does not affect the outcome of any future trial. Of course, maybe this isn't true if you don't set the experiment up right, but it's usually, the independence usually feels pretty good. I think flipping a coin is independent. We could take many experiments. We accept the independence. We live with 2 uncertainties. This is true with the Monte-Carlo simulation. I know you don't know even what it is yet, but it's a little ahead of it. Yeah, so then we take these independent, we do these independent trials, flip a coin 1,000 times, do a test in the lab 80 times, and count if an event happens. Say I do a test in a lab 80 times. I'm waiting for a certain event to happen. Say it happens 10 times. I might say the probability that event happens is 1/8. That's the idea. You take the average. So we live with two distinct uncertainties. The first is that we will never expect that our estimate, the 1/8, is the exact probability. This makes no sense. It's an approximation. It's a point along the way in the limit that the law of large numbers provides. We accept also a small probability that we may be way off, because a limit really doesn't say anything about the probability at a finite n, we'll see there are intermediate results before the limit that do. And we're going to work with those. But even those are only give probabilistic sort of intervals for the estimate, okay? So we have two dimensions of error, if you will. One is the actual estimate could be off a little bit, and the other is there's this probabilistic feature that we could be off by a lot. So you make both of them small and you feel pretty good. That's the idea. Any questions? All right, so here's wanted to do very simple ones at first. And then, so this is just the Bernoulli Pebble experiment. This, I made it 2 out of 9. So figure 200 black pebbles and 700 other pebbles. And I'm picking, and I just want to see how many black ones I get. Yeah, question? Are you losing me?
Yes.
Back? Am I back?
Yes, you are. Yes.
Okay, thanks. Thanks, Amir. All right, so in here, all we do is we repeat, I did 10,000 of these, and I generate a uniform vector here of numbers that are random between 0 and 1. I come in this loop, I check, is it less than 2/9? I set it to 1, that means it's a black pebble. Otherwise, it's not. I set it to 0. And then I do this pretty lazy computing the average. There's a more clever way to do this where you're not actually summing the average every time, but lazy style here, it's okay. And I go and I look at my tail. What's my last computation here? I get something pretty close. It's only off in the 3rd digit. All right. So pretty good error, right? Here's my error, 0.003. Relative error is about 1.5%. Can you hear me?
Yep.
Thanks. We should, okay, we give it. Okay, so here's a picture of the average. I find this interesting. I mean, when you know the limit and you see these pictures, you feel good. You can see at first, probably looks like the first one was black, and then maybe the second one wasn't. Yeah, probably something like that. The second one wasn't, the third one wasn't, it looks like fourth one wasn't. So the average is getting pulled down. Maybe there's some in here that are both, gets pulled down. I could go look at the data. I have it, but in R, it's all there. I don't have it anymore, but I could have looked at it at the time I did this. But there we have it. This is the tail. This is like the last 1,500 of them. And one thing to notice is there's a lot of noise still. There's also this other feature of drift, which is another topic altogether. Something else I want to talk about is drift in these kind of things. But that will be for next Wednesday. No, I'm just kidding. That's for another semester. Okay, so we're here. One nice thing about this tail thing is you can kind of see the window and see the epsilon here, your limit. It's like 0.226 something, and then 0.225. It actually looks like it's going up a little too far. We want to be down at 0.222, right? 0.223. So it's still not settled out yet. All right, so here's the math. I don't want to give anyone indigestion though. Are people eating?
I am, but this is not at all giving me.
Oh,
indigestion.
okay. I didn't think this was going to stress you out.
It's
I was
very,
worried.
you know, the cerebral thing really helps.
Oh, okay, good. Yeah, it helps me too. It helps with joint pain, I find.
Yeah.
All right, so in our simulation, we found an estimate for 2/9, and we had 0.2254, which was just the last one, the last average. How do we interpret this really though? Suppose we're getting something that we really don't know what it is, and we get this number. What do we make it? Do we just say this is the number? A lot of people do that. we may be content to stop here. We found a point, quote unquote, point estimator. Indeed, simulations are often run to corroborate other evidence of something, like something in a lab or some equation you worked out. So sometimes we're satisfied with this, but we can say a lot more. And this is where I kind of went into this instead of just doing more, appealing maybe to the non-math people type examples. But yeah, I went into this a little. So speak up if you have questions, and let me know if it's going too slow. So there's many routes to take to bear down on that number and get some kind of result. We could use the central limit theorem or the law of large numbers. Both, what I mean by that is, since they're limits, they don't really say anything about a finite n. So we can't use just the limit to say very much, but I mean the intermediate results that led to those limits give a lot of bounds on things. So we can use a lot of those results to bound at a certain n. We're going to consider one that's the law of large numbers style in the spirit of Jacob Bernoulli, and which will be the following. It's called Chebyshev's inequality. It came about in the 1860s by the Russian monster of a mathematician, Chebyshev. He had this proof. I mean, the usual way we see this this inequality now is as I'm jumping ahead. So the usual way to derive the inequalities in 2 steps for today, because all the examples we're doing, we have discrete random variables. A discrete random variable is defined to be any variable that takes on a countable number of different values. So it can take on all integer values, it can take on a finite set of values, but it can't take on any uncountable number of values. Its expected value can then be represented by a sum, possibly infinite. Even if we're mainly we are mainly interested in indicator random variables, which are very discrete because they're only 0 or 1. So mainly we want to apply this inequality to such variables that are usually either 0 or 1. Okay, so we say X is a Bernoulli P random variable. If the probability it's 1 is P and probability it's 0 is 1 minus P. I bet now you know why it's called Bernoulli. All right, look, so this was, I typed this in LaTeX and then it's a little bit dense, but I think we can go through this and a little bit. So, yeah, let me get so here's the main theorem. If I have a positive non-negative random variable, which just means the probability it's non-negative is 1, then the probability that it's greater than any A is less than or equal to its expected value divided by A. This is little bit not intuitive, but the proof is right here. It's, I think, very straightforward. So probability X is greater than A, I sum the mass function starting bigger than A. That must be less than or equal to this factor X over A times the mass function over the same set. Why is that? Why can I multiply inside here by X over A and get this inequality here?
This is a positive.
Okay, yeah, good job, because it's bigger than 1, right? X starts at A.
It's greater than A, yeah.
Right, X is greater than A, so it's always bigger than 1. And also the other key thing is PX is positive, right? It's or non-negative. It's so I multiply non-negative things by things that are bigger than 1 and add them together, I get something bigger. That's the key step, I think. Then I could just go down and start at 0. Say again?
Sorry for interrupting.
No, it's no problem.
Is the equality when X equals A, but X can't equal A? So is it when P of X is 0, or does it not matter?
A has to be greater than 0. We say X is greater than A. I think it doesn't matter if I make it X greater than or equal to A.
Okay.
Yep, it shouldn't matter. So then I'm here. right? That's the same as that. And then I can just go down and start at 0 now and keep x over a. Now x over a may be less than 1, but it doesn't matter because I've already established this inequality here, and now I'm just adding more positive numbers. They may be very small, but it doesn't matter. This inequality, weak inequality holds, and I get this. That is the definition of E of x if I pull the a outside the sum. That's the proof of the actual theorem. What's known now as Chebyshev's inequality is just a corollary of this. We now consider the random variable x minus its mean in absolute value. So in other words, the random variable becomes the deviation in absolute value from the mean. And I want to consider the probability, and then a becomes k sigma, k standard deviations from the mean, sigma being the square root of the variance of x, also the variance of, yeah, just the variance of x, okay? Is enough. So I have this is equal to this, square both sides, positive numbers. I square them, this is true. I had to make, this is maintained, this is equal. And then this is less than this from Chebyshev's inequality. The reason is, you see why? I just took the expected value of this, put it on the numerator, and divided by a on the, over here. But what is the expected value of the numerator? Okay, it's the expected value of the difference of x with its mean squared. That's the variance. So that's sigma squared cancels 1 over k squared. So the mean and the variance do not result over here if you formulate it right. All right, so you made it through the worst part. So thus the probability that any random variable exceeds its mean by more or less than k standard deviations is bounded above by 1 over k squared. Yes, okay. So for example, if I have a normal random variable, the probability it's within its mean, 2 standard deviations of its mean is known to be 0.955, something like that. Chebyshev tells us it must be greater than 0.75. The power is, it's very conservative, but the power is there was no information needed. I can now go out into the wild, perform Monte-Carlo simulations without knowing the distribution, as long as it's reasonable to make certain assumptions about independence and things like that. Okay, so I computed the sum for some examples here to show you the comparison. If actually this shouldn't be sigma, this is a mistake here. This should say k. This is if k equals 1. So if I'm k, 1 standard deviation away from the mean, 2, 3, 4. So Chebyshev doesn't tell me anything if I just want to know the probability I'm within 1 standard deviation. It tells me it's 3/4 that I'm within 2, 91% within 3, 93% within 4. And if I know it's normal, and it doesn't matter what the mean and variance are, then I know exactly even any fractional amount, because I know the distribution completely. But you can see it's much better, and you get, this is essentially describing the normal curve here. All right, very good, thanks. So thanks. Okay, so any questions? We have time, a little more time. All right, so how do I interpret the results then using the inequality? We see the possibility of taking the simulation output, probably the final average over all trials, and getting a confidence interval now using Chebyshev's inequality. You notice a lot of times you're reading things, I think many of you have seen this, where they say, well, in the limit it's normal, so, and then they go off and start to make assumptions everything's normal. This is, it's okay, I mean, but it's you know, leaves something to be desired. I mean, it's a good argument, but it doesn't feel like math a lot of the time. So I think we get a lot closer with Chebyshev, even though it's cruder. So represent the outcome of the ith trial with a random variable xi. So this is it. We have to identify a variable xi that's going to be associated with the outcome. So for example, in the one we did with the pebbles, xi is 1 if a random number between 0 and 1 is less than 2/9, otherwise it's 0. For many applications, xi is an indicator variable. Because if it is an indicator of random variable, its expected value is the probability, then also the expected value of the mean is the probability. That's easy to show. So X bar is an unbiased estimator of the probability. This is good. This is always what we want in statistics. And we also want minimum variance. So we also have the variance of X bar is equal to the variance of Xi, which is 1 minus p all times p, but we might not know what p is, divided by n, but it goes to 0 as n gets large. Okay, so here it is in nicer math notation. I have these random variables, let's call the expected value mu, the variance sigma squared. I have a sample mean. It's easy to show these things that the expected value of the mean is the same as every xi, and the variance is the variance, but now it gets divided by n, and that's the great thing. It gets divided by n, so it's decreasing. This is the other good thing about an estimator: low variance. You want the bullseye to be, you want your target to hit the bullseye. That's the center of mass, but you also don't want a lot of variance. You would prefer something that was biased, that had a very low variance, over something that is unbiased with a huge variance, usually. So applying Chebyshev then, and noticing that the variance for a Bernoulli random variable is less than or equal to a quarter. Can anybody tell me why this is less than or a quarter? See if any of the math professors are still here. I can't see anyone. So
because it's bounded above by 1/2 of 1/2 times 1/2.
Yeah, right. Andrew, so yeah, it's a downward parabola, right? And the apex is at 1/2 here. So right. So at 1/2 it's a quarter, right? So we can strengthen the inequality above, and maybe even more important, avoid estimating sigma, which we don't know. But we can say sigma squared is always less than or equal to a quarter. Sigma is always less than or equal to 1/2. So in this equation here, I will put in 1/2 for sigma and strengthen the inequality. Sometimes, okay, so we're home. This is home right here. Looks like home. Looks like home to me. Probably doesn't look like home to you yet, but maybe. So the probability that the sample mean minus the true mean is greater than any number, any k positive, over 2 square root of n must be less than or equal to 1 over k squared, with the only assumption of independence, which I feel fine with personally. So now I can pick k and n to give, actually you can put any k in after the fact to ascertain the probabilistic error, but I can pick a k ahead of time and then pick n to give an accuracy. So in the Pebble simulation, we didn't do that. We just had 10,000. We set k equal to 5 just because I picked 5, and I get a 96% confidence interval is 0.2004, 0.2504. We computed the true error because we knew the true probability, but usually we don't. So usually we're happy to have a confidence interval rather than a point estimate. Doesn't tell you very much. 0.0032, much smaller than the radius. The true mean is snuggled right in the middle there of that interval. It's protected. And the reason is Chebyshev's bound is conservative. Any questions on this one, or? All right, you made it. I think you pretty much made it through the math, I think. so setting n, then we just set, it's simple, right? We can just, we have this simple equation, algebraic inequality. We have this inequality, and we could just set k what we want, and based on a confidence interval we want, and then we can set n based on the k and the radius and everything. So I did a table here for what you should set n to based on the confidence level you want and the radius you want. On a laptop, just like a $700 laptop, the last one can give you problems in R, actually. So even for something fairly simple. So, but obviously you can go much more accurate than this on fast computers and servers and things like this, supercomputers. Any questions on this? I feel I'm rushing a little now. All right, excellent. Thanks for the feedback. All right, so we'll just do some examples. And if I want to calculate this integral, 0 to 2 e to the cos of x cubed dx, which is not on your honors calculus midterm, you can't do it analytically, right? You could use Simpson's method or many other methods, but one option is to use a Monte-Carlo simulation. I take a rectangle that contains the integral, the definite integral, and I shoot at it, at that rectangle, and I count randomly, bad shot, and I count how many of the shots fall under the curve. Okay, so if we do this, so it's 3.68. So if I do this, you have to think about how to set it up first. I think that's usually the thing. We just take two random numbers like this between 0 to 0, 3, and I will just set wi equal to 1 if yi is less than f of xy, and otherwise I'll set it to 0. And the expected value of 6wi, then the area of the rectangle times the probability I land in the rectangle will give me the integral. So we notice that since the expected value of the mean is the expected value of each element, I have expected value of 6 wn bar is also I. And now the variance of 6 wn bar is a little different than the previous example because of the 6. It magnifies the variance. I get 36 variance of wn bar. But wn bar is just a Bernoulli random variable, right? So I can bound that. So I get 36. Variance of wn bar is sigma squared over n. So I get 36 over n sigma squared. And I bound sigma squared again by a quarter. And so I get 9 over n. So the variance of the estimator for the integral is 9 over n. The standard deviation is 3 over the square root of n, which you see 3 over the square root of n times k here, just like it should be in the inequality. So then over here, I get less than 1 over k squared. I pick k equals 5 because that seemed like a nice level here. And I get a 96% confidence interval, level interval when n is this amount. I have to solve this. It's a little different because of the 6 out front. So I need 2.25 million. So I did this exactly with 2.25 million. This is R. This is doing vectors of these, so I'm doing them all at once. And it's very short and very easy to do once you're used to this. At the end, I just use the mean command to compute the mean, and I get correct up to 2. Anyway, 3.68, 4349, which otherwise I wouldn't be able to do if it weren't for Wolfram Alpha or, Mathematica or something. All right, so when I did the analysis, I get 0.01 for the interval, and 0.368 is actually much better than that. Okay, so the actual error is much smaller. I didn't actually show what the error is here, but it's a bit smaller. All right, so I just want to do a couple interesting examples, and then that's it. So sorry for taking so much time. Are you still there?
I'm here.
Yep.
Okay,
all
thanks.
here.
Appreciate it.
You have an
I
hour.
appreciate it. I just, yeah, I got out with like 16, 17 minutes. I didn't want to take the whole time though, because we want to talk and things, but so I have a little more, just a little more, and this will go fast. So for the next one, think of a game, the sub game of craps. So in craps, you roll the dice, and if you get one of these sums on the first roll, this becomes called the point. And then you keep rolling until you either hit the point or a 7. The other rolls on the first roll lead to other outcomes. We won't deal with that. It's not interesting for us as probabilists. So we would like to compute the expected number of rolls conditional on winning versus on losing. But as a warm-up, let's just compute the probability of winning if the point is 9. So I'm just considering this sub-game after the first roll happens and I get a 9. So really, I want the probability of rolling 2 dice and finding the probability, I get a 9 before a 7. So typical outcomes I show you here. The zeros mean another. All right, so the probability of a win is, so I have a lower probability to win than lose. This sounds typical in a casino or life, maybe you might argue. The probability of win is accomplished by adding the probabilities of all the outcomes. There's an infinite number of outcomes, you should realize, but it is a countably infinite set. I have 2 times the cardinality of the natural numbers, something like that, right? Because I can end with a 7 or 9, but that's it. So this is doable. And it's a one-line thing to just compute it with a geometric sum. But this way is better, though. This is a better way to do it, I think. Another way to compute the win probability is argue that the game, you can only win, that the probability the game ends on a 9 is the same that it ends on a 9, given that I know I just rolled 2 dice and I rolled either a 9 or a 7. It's the probability that's a 9, knowing that I rolled either a 9 or a 7. This should be true because we should be able to ignore all the previous rolls in determining the probability of whether we rolled a 9 or a 7. This is sort of subtle, and this is why I thought this was a good thing to do a simulation of, which I always seem to trust. Whereas I don't totally trust it. The probability game ends in a 9 versus ends in a 7 is just the probability of rolling a 9 conditional on rolling a 9 or a 7. So then you use your base formula here, and I'm down at the bottom thing. I can't use the pointer to. Probability game ends on a 9. Probability 9 given I roll a 9 or a 7. That's just those probabilities of the rolls like that, and I get 2/5. I did a simulation of it, and I get very, very close, right? I get actually 2 orders of magnitude better than the Chebyshev tells me I'm going to get. So it works. Also, for you coders out there, this is a much better way to compute the average. You can now do it every iteration with a big number. You take the previous average, right, which would be the average at game -1. You multiply it by game -1 to get the contribution from the first n-1, game -1 outcomes, and then you just add the latest, and then you divide by game, right? So that's the right way to do this, not the lazy way I did it the first time. All right, so here's a picture of it. I just like looking at these pictures. I'm not sure why. But you see it? Sorry? Question? Uh-oh.
No, I think we're good.
All right, did anyone have a question? It's okay if we don't finish, if you want to talk about it. Okay. Very good. So I go through this and analyze it. We'll skip this. It's the same thing. Like I said, if you want this after you want to see it, let me know. It can be helpful document, I think, going forward if you do this stuff. Maybe not. Maybe there are better ones. Okay, so now we want to get to the one that was interesting. So we found the probability of winning is 2/5. We actually don't need this for the other thing. It's just a warm up. What's the expected number of rolls given we win? So let's let R be the number of rolls in a random game and let W be the event we win. So it ends in a 9 rather than a 7. L is the event we lose. It ends in a 7 rather than a 9. E of R is easy to find because it's just the event the game ends in a 9 or a 7. I have no problem with this one at all. R is a geometric random variable with probability 10 over 36. So the expected value is the reciprocal of that. It's 3.6. But when I first saw the problem on the conditional ones, I didn't understand it. And my intuition led me in the wrong direction. I thought E of R given W would be less than E of R given L, because the 7 usually occurs faster than a 9. Its probability is bigger, so it usually occurs sooner. The expected number of rolls until a 7 occurs is 6. The expected number of rolls until a 9 occurs is 9. So why wouldn't you assume that the expected number of rolls given you win is bigger, even if it's not 9, it's bigger than the expected number of rolls you lose. Instead, they're the same. And I think the idea is that if the 9 won, it was a good 9, right? It was a low 9. And if the 7 lost, it was a slow 7, you know? So somehow it works out that they're the same. Here is the explanation, which I at times still don't really feel too well. Because the rolls are independent, winning doesn't depend on the number of rolls. So in other words, I could roll 7 times and get other things. And then the 8th one, you would argue, everybody would argue, the probability you win or lose is the same. It's just the probability I roll a 7 or a 9. So then the probability of W given R equals little r is just the probability of W. It's just 2/4. Now here's the thing, independence in probability is reflective. The probability, if A is independent of B, B is independent of A. So if the probability of winning, given that you know the number of rolls, is just the probability of winning, then the probability that the number of rolls is something, is little r, given that you won, should just be the probability that the number of rolls is r. Okay, so I wanted to test this. So basically this just says that this is the definition of conditional probability, and I can replace this up here with, in theory, with this. And I have that the expected number of rolls given a win should just be the expected number of rolls. So it shouldn't matter whether we win or lose. ER is equal to 3.6 is equal to ER given win, also equal to ER given loss. It's enough to check one, because if you know one, you know the other by the law of total probability. All right, so here's the simulation. It's a little, it's not, you just have to count the rolls if it's a 9. That's the only really difference, is I keep this vector here that counts the number of rolls if it's a 9. And you have these 2 loops because you have to roll for, you know, an unspecified number of times. And I get 3.607136. Very helpful, by the way, for when you are trying to understand something and you're not sure in math. I have many times, I use it in linear algebra and in probability a lot. I use numerics to just make me believe something. I say, okay, well, it said it's true. So it just somehow reinforces the theory. It's not a replacement for it, but I find it's a effective sort of bolster. This is a little printout of the win roll count, which just gives you a 0 if you don't win, but just sort of shows you the spread of the values. So some of these were pretty high. There's a lot of 1s. This is when the number of rolls until a 9 happened before a 7, in the case that it happened before a 7. Interpreting the results, there is a point to make about this. In Chebyshev, we need to know the variance of xi, and in the indicators, I bound them by a quarter. Here I don't have an indicator, right? I have an expected value of an integer, and it could be infinitely large, really. I don't even know if it's finite, although I do know it's finite, but you know, you don't know a lot about it. But certainly, the whole point I'm doing this is to find the expected value of R given a win, and you can't know the variance if you don't know the expected value. So you're stuck here, and you would have to estimate this somehow. However, you can also slug this one off as just saying this is one of the ones that I'm really just verifying a result from theory. So I'm not so concerned about finding an interval. I just want to verify that the theory looks right. I have one more. I think maybe we'll just do this one more. It'll just take a second. So say I have two uniform random variables, two random variables, one's uniform, the other's exponential. They both have a mean of 1. Here's a picture of their densities down here. And say I want to find the probability the uniform is less than the exponential. So the densities represent sort of the likelihood that the variable falls in any of these intervals here. I integrate over any interval I care about, and then I have the probability that the variable's there. Well, it's not obvious. There's no way you can do this by eyesight, what this probability is. But we have a little theory that says if they're independent, then I have a joint density, which is the product of their marginal densities. There's a little subtlety to that, not much, but a little subtlety around the integration. And at the bottom line of it, in a mathematical setting, you can get, it probably does need some kind of measure theory or something to do it in its full proof of that. But I think it's very reasonable. So what I have here is I have probability x less than y is the integral of the joint density over the region of interest, which would be x less than y and y less than 2. A y has to be greater than 0 as well. I didn't write that. And then I can split that. Now I've inserted the joint densities in here, but because x is only 0.5 from 0 to 2, I broke it into these two pieces. So it's really the probability x is less than y where they range between 0 and 2. And then plus the probability y is greater than 2, because then x has to be less than y. You want to be careful not to bring the x over here because it can't be over here. And this is not really the joint density anymore. So if I do this, I can evaluate these. These are both easy to do, integration by parts, et cetera. So you get things involving e squared and e cubed, and you get this. So, so we noticed that if we can do a very simple simulation of this, that's very simple, and get the number. And did I do it? Yeah, look how short this code is. What I like about this just does what it says. Compute a 0, 2 uniform, compute an exponential 1. Is it less? Yes, increment the counter. I have a Bernoulli random variable. This is my estimate. It's very close, actually, so I didn't do the analysis on this. I just wanted to point to this remark. You might think this one doesn't have any purpose, but often the densities are complicated, and when you multiply them, they're impossible to integrate. It could be over multiple dimensions. You need Monte-Carlo or some numerical methods. So it's even conceivable, I surmise here at the end, but I'm not sure anybody's ever done anything like this, that you would see an integral and say, well, I don't know how to solve that integral. Let me represent two factors as densities and then use a Monte-Carlo simulation to go back and get the integral. This is a picture of the convergence of the, and there's the books that I've used. Bernoulli's book treatise is pretty short, but and not bad to read, actually. It's pretty interesting. He talks a lot about religion and other things too in it. And then William Feller's book is an amazing book. I read it this summer really closely. I've been trying to read it and always thought it was a little hard, but it's not hard. And then the book I use for the course.